Alright, so this time we're going to take a look at section 15.7. And this section deals with triple integrals and cylindrical coordinates. So we're going to take a look at what it means to represent a point in cylindrical coordinates. Let's say you have a situation like this. You might have a point P somewhere in three-dimensional space. We're going to take a look at what the projection of that point P is in the xy plane. Maybe that projection looks something like this. Now, in rectangular coordinates, this point P has coordinates x, y, and z. But in cylindrical coordinates, it will have coordinates r, theta, and z. Now, r is going to be the same type of r that you see in polar coordinates. Theta will be the same kind of theta you see in polar coordinates. It's just going to be the polar coordinate representation of this point in the xy plane. So you look at projection of the point P. This distance will be r. Here you'll have your angle theta. You have x and y here, and then here you have your z. And so let's formalize this in a definition. So in the cylindrical coordinate system, we have a point P in three-dimensional space. It's going to be represented by the order triple. R, theta, z, where r and theta are the polar coordinates. Of the projection of the point P onto the xy plane. Now z is going to be the directed distance from the xy plane to P. And so we start thinking about conversions. How do you convert from one set of coordinates to the other? And so we can think about what it means to convert from cylindrical to rectangular, or from rectangular to cylindrical. So if we're going from cylindrical to rectangular, we're going to know r, theta, and z. Now, if we know r, theta, and z, first off, if this distance from here to here is x, then we know that x is the same thing as r cosine theta. And if this distance is y, we know that y is equal to r sine theta. So these are familiar equations that we saw when looking at conversions from polar to rectangular. And then if we want to go from rectangular to cylindrical, we'll see some familiar equations here as well. Because once again, if this distance here is x and this distance here is y, X and Y are the lengths of the legs of this given right triangle. So x squared plus y squared is equal to r squared. We also know that the tangent of theta is going to be y over x. And finally, z is equal to z. And so let's take a look at a couple of examples. So this example will contain a part A in which we are going to go from cylindrical to rectangular coordinates for a given point, and part B will be a part where we go from rectangular to cylindrical coordinates for a given point. So find rectangular coordinates for the point. With cylindrical coordinates. And these cylindrical coordinates are 2 pi over 3, and 1. Now in part B, we're going to find cylindrical coordinates. For the point with rectangular coordinates. And these rectangular coordinates will be 3, -3, and -7. All right, so let's take a look at how part A works out. And so for part A, keep in mind that our R is 2. Theta is 2 pi over 3, and z equals 1. We're converting from cylindrical to rectangular coordinates. So we start out with this x equals r cosine theta. Well, if we know that r is 2 and theta is 2 pi over 3, that means x is 2 times cosine of 2 pi over 3. Now, cosine of 2 pi over 3 is a -1/2, so x is equal to 2 times a -1/2, which means x is -1. We then take a look at what y is, but we know y is r sine theta. Again, we plug in 2 for r, 2 pi over 3 for theta. So we have 2 times sine of 2 pi over 3 is equal to y. And sine of 2 pi over 3 is square root of 3 over 2. So y is 2 times square root of 3 over 2, which means y is the square root of 3. And our last part to all this is the easiest. We have z equals z, which means, okay, z is equal to 1. So our representation for this point in rectangular coordinates will have a -1, square root of 3, and 1 as the x, y, and z respectively. We next take a look at part B. And in part B, we're going from rectangular to cylindrical coordinates. But let's recall that if these are the rectangular coordinates, we have x equals 3, y equals -3, z equals -7. And so we know that r squared is equal to x squared plus y squared. But we have x equals 3, and we have y equals -3. So r squared is equal to 3 squared plus -3 raised to the second power. But this gives you 9, And this gives you 9 as well, so 9 plus 9 gives you 18. Which means r is the square root of 18. But if you think about the square root of 18, you could write that as square root of 9 times 2, which is root 9 times root 2, or 3 times square root of 2. So one way that we can represent r is as 3 times the square root of 2. Now, we also have to figure out theta, but we know tangent theta is y over x, negative 3 over 3. But then that means that the tangent of theta is equal to negative 1. And so you might think about, well, what sort of angle are we going to be looking for here? And if you think about the projection of this point onto the xy plane, you'll notice that the projection, because x is positive and y is negative, that projection is going to be in the fourth quadrant. So we're looking for theta to be a fourth quadrant angle. And what's more, given that the tangent of theta is equal to negative 1, we would expect opposite leg or an adjacent leg to have the same length. This would be labeled as negative 1, this is positive 1, but that gives you a 45-degree reference angle. So full revolution minus 45 degrees is 315 degrees, which corresponds to 7 pi over 4 radians. Now, you could take theta to be 7 pi over 4 plus 2 pi n, where n is any integer, and that would also be a viable theta given this r. And then finally, we have z equals z yet again. This time z is equal to negative 7. And so the coordinates, or one set of coordinates that we could use to represent this location, but in cylindrical coordinates, would be 3 times square root of 2, comma 7 pi over 4, comma negative 7. Now, notice that the title of the section is Triple Integrals in Cylindrical Coordinates, so we need to start thinking about triple integrals at some point. And so we're going to be thinking about a solid region R. This is going to be a type 1 solid region. And we're going to be interested in the projection of that region onto the xy plane. We'll call it projection D. So we want E, once again, to be a type 1 solid region whose projection D onto the xy plane is conveniently described in polar coordinates. Okay. Well, in particular, we're going to suppose f is a continuous function so f will be a continuous function of 3 variables. And we're going to define E as follows. So E is going to be the set all points x, y, z such that x, y is in this projection D, and z is going to be bounded by u1 of xy and u2 of xy. Now, D is going to be represented in polar coordinates, though. excuse me. And the way we're going to do that is we're going to say D is going to be the set of all points R theta, such that theta is going to be bound by alpha and beta. So we'll have these constant bounds on theta. And R is going to be bounded by h sub 1 of theta and h sub 2 of theta. Right, so that's going to be our description. So what we're going to be really focusing on is what is the triple integral of this function f over the solid region E. Well, the leftmost integral is going to have bounds of alpha and beta. The middle integral will have bounds of h1 of theta and h2 of theta. And then the inside integral, normally we would say that the bottom limit of integration will be u sub 1 of x comma y, top limit u sub 2 of x comma y. But if we're doing all this in terms of cylindrical coordinates, then we're going to want to represent this u sub 1 of x comma y as u sub 1 of r cosine theta comma r sine theta. And we'll do a similar thing for the top limit of integration with the u2. Now, the function that we're integrating is f of x, y, z, but again, we're wanting to represent this in terms of r theta and z. So we would have, instead of f of x to start, we would have f of r cosine theta. For y, we'd have r sine theta. And then z, well, z is still sitting there. Now, the last part is to figure out what dv is going to be. And I'll go ahead and tell you that the dv will be r dz dr d theta. R dz dr d theta. Now, if you're wondering where that extra r comes from, it's the same kind of idea that we saw when we looked at double integrals when we converted from rectangular to polar coordinates. Remember that the dA was r dr d theta. So if you were to take a look, let's say, at a triple integral like this and keep it in terms of rectangular coordinates, then presumably this inside integral, you could take a look at f of xyz dz, and then you'd have your u sub 1 of xy as your bottom limit of integration, u sub 2 of xy as your top limit of integration. And then once you integrate this, you can say, well, I've got this region D that I'm going to take the double integral of this thing over, and then you'd have your differential A on the far right. But remember, if you're doing a conversion from rectangular to polar coordinates with your double integral, this double integral over D, that's going to be represented in terms of polar coordinates. It's going to be represented in terms of bounds on r and theta. And so the dA would be your r dr d theta. So if you take dz times dA, that's your dv. But then this would be dz times r dr d theta. Just put a different little order on r and dz, and this is what you have here for your dv. So it's not exactly the nicest looking representation in the world, but it works, so there's something to be said for that. So let's consider an example. And in this example, we're going to have a solid E that lies within a cylinder. So Now let's say that cylinder is x squared plus y squared is equal to 1. Let's say it lies below the plane. Z equals 4. And let's say it lies above the paraboloid. Z equals 1 minus x squared minus y squared. Now, we're going to have a density function that is going to be defined over the solid. And the density, at any point, is going to be proportional to the distance from the axis of the cylinder. So given some sort of point that's in the solid, you're going to want to measure the distance that point is from the z-axis. And so our goal here is going to be to find the mass of this solid E. So to do that, we're going to have to figure out the triple integral over E of our density function. And I'd like to get an idea of what this solid looks like. And so the cylinder, x squared plus y squared equals 1, is going to intersect the xy plane in a circle like so. Circle of radius 1, center at the origin. And then if we take a look at our paraboloid, z equals 1 minus x squared minus y squared, one thing you might notice is that this is going to peak out at z equals 1. But then if you take a look at the intersection of this paraboloid with the xy plane, you would have z equals 0. If 0 is 1 minus x squared minus y squared, that means x squared plus y squared equals 1. So the paraboloid is actually going to intersect the xy plane in a circle. Now if you look at the intersection with the xz plane, you would have y equals 0. The intersection would then be z equals 1 minus x squared, which is a parabola. It looks something like this. And then if we take a look at the intersection in the yz plane, so if x equals 0, z equals 1 minus y squared would be that intersection. Once again, we're getting a parabola. And so if we were to make this, we have sort of the skeleton of the paraboloid right now, so if we were to sort of fill this out, we would get a picture that maybe looks something like this. All right, so now z equals 4 is also going to be a boundary. It's top bound for this solid. So I got 4 units on the z. And we're going to take this circle that's in the xy plane, shift it up 4 units, and so you get a picture that looks something like this. There we go. So And then we'll draw our little circle like this. And now we can draw these little sides that will finish out our solid. So the solid E is really the cylinder with this little part of the paraboloid kind of dug out of the bottom. Now, we're also going to need to know something about the density function. And so if you think about what the density function is, well, it says the density at any point is proportional to the distance from the axis of the cylinder. So if we were to take a look at, maybe this is a point that's in the cylinder, we trace this back, take a look at the distance between that and this axis. If this point has coordinates x, y, z, then this point, since it's on the z-axis, will have coordinates 0, 0, z. And so finding the distance between these 2 points, d is going to be the square root x minus 0 squared plus y minus 0 squared plus z minus z squared. In other words, the distance is just square root of x squared plus y squared. And if the density is proportional to the distance from the axis of the cylinder, density is proportional to the distance, that means that our rho is going to be thought of as k times the square root of x squared plus y squared. Now, in terms of cylindrical coordinates, we know x squared plus y squared is the same thing as r squared. Square root of r squared gives us r, so we can think of our rho as k times r. Now, we also have to have some sort of representation, some sort of description for E. And so if you think about how to describe this solid E, first off, let's keep in mind that theta is going to range from 0 to 2 pi. So when we go to write down our description, we're going to have points r, theta, and z, such that theta ranges from 0 to 2 pi. If we take any point that is in the solid here, project it down onto the xy plane, then we know that that point is going to be anywhere from 0 to a maximum of 1 units away from the origin. So we're going to have bounds on r between 0 and 1. And then z, if you think about the bounds there, top bound is going to be z equals 4. Bottom bound is z equals 1 minus x squared minus y squared, but that could also be written as 1 minus r squared. So 1 minus r squared will be lower bound on z, and 4 will be our upper bound on z. And from there, we're going to be able to set up a triple integral that will represent the mass of this solid. All right. So to get the mass, we're going to have the integral. Leftmost integral, 0 to 2 pi, will be our limits of integration. In the middle, we'll have 0 and 1. On the inside, we'll have 1 minus r squared, and we'll have 4. Now, it's this density function that we're going to need to integrate. So think about if we were to take the triple integral over E of rho dv. Well, the dv in terms of cylindrical coordinates is r dz dr d theta. So if we're going to have a times r dz dr d theta, this is our dv right here. And that's going to give us a kr squared that we're going to end up integrating with respect to z. Now, when you integrate kr squared with respect to z, we get kr squared times z. And we'll have to plug in 4 for z and then subtract what we get when we plug in 1 minus r squared for z. So when you plug in 4 for z, you'll get 4kr squared. Subtract what you get when you plug in 1 minus r squared for z. But then if you take a closer look, you've got your 4kr squared here. You'll have a negative kr squared from here. That'll give us 3kr squared. And then we'll have a negative kr squared times a negative r squared, and that'll give us a plus kr to the 4th. And we'll let's write this a little bit better. And so now we integrate the 3kr squared. That gives us a 3k times r cubed over 3. It's kr cubed. And then the kr to the 4th integrates to k times r to the 5th over 5. Or 1/5 k r to the 5th. Now the limits of integration on r were 0 and 1. So if we plug in 1 for r, k times 1 cubed gives us k. 1/5 times k times 1 to the 5th gives us a 5th k. So you have a k plus a 5th k gives you a 6/5 k. Subtract what you get when you plug in 0 for r. Well, that's just going to give you 0. So we're going to have m is integral 0 to 2 pi 6/5 k d theta. Integrate this with respect to theta. And we'll get a 6k over 5 times theta. We'll plug in 2 pi for theta. Subtract what we get when we plug in 0 for theta. You get a 6k over 5 times 2 pi, and that's going to give you a 12 pi k over 5 as the mass. Now, there is one more example I'd like to show you. With this example, we are being asked to evaluate a certain triple integral. Leftmost integral has limits of integration -2 and +2. The middle integral has limits of integration of negative square root of 4 minus x squared and positive square root of 4 minus x squared. And the inside integral has limits of integration of square root x squared plus y squared and 2. And what we're going to be integrating here is x squared plus y squared and the order of integration will go z, then y, then x. Unless, of course, we think of this in terms of cylindrical coordinates. Now, in terms of cylindrical coordinates, your x squared plus y squared is going to be the same thing as r squared. So you'd have an r squared here, square root of r squared here, or r, still have the 2 up top. And then we start to take a look at the limits of integration on these two integrals. These limits of integration describe a certain region, and that region is going to be the projection of the solid E onto the xy plane. The solid E given by basically, or described by this full set of limits of integration. And so we start to think about what exactly would the region that's defined by these limits of integration actually look like. Well, we see that -2 and 2 are going to be bounds on x. And then negative square root of 4 minus x squared and positive square root of 4 minus x squared are bounds on y. But y equals square root of 4 minus x squared is the top half of a circle of radius 2 centered at the origin. And y equals negative square root of 4 minus x squared is the bottom half of that same circle. So we're able to describe our projection of the solid onto the xy plane. It's bounded by this circle of radius 2 centered at the origin. So if we call this region D, D can actually be defined or described very conveniently in terms of r and theta. So r is going to be bounded by 0 and 2, while theta is bounded by 0 and 2 pi. And now what this means is that when we go back to this original triple integral, this leftmost integral, we can put 0 and 2 pi as limits of integration. In the middle, we'll have 0 and 2. On the inside, square root of x squared plus y squared, square root of r squared gives you r. Top limit is 2. X squared plus y squared is r squared. And then your dz, dy, dx is the same thing as dv. But remember, earlier I mentioned that in terms of cylindrical coordinates, your dv is the same thing as r dz dr d theta. And of course we can multiply the r squared and r to get r cubed. And we'll finish this out over here. So this triple integral that we have looks slightly better in the next step, because we'll have the r cubed dz dr d theta. Now, we have to integrate r cubed with respect to z. And that'll give us r cubed times z. We'll take this from z equals r to z equals 2. Plug in 2 for z, you get a 2r cubed. Subtract what you get when you plug in r for z. R cubed times r gives you r to the 4th. Now, if we integrate this with respect to r, I have 2 times r to the 4th over 4, that's a half r to the 4th. Then minus a 1/5 r to the 5th. Now we can plug in 2 for r and then subtract what we get when we plug in 0 for r. Plugging in 0 for r will just give us 0. And so this is the integral of 0 to 2 pi. 2 to the 4th, 16, times a half gives you 8. 2 to the 5th is 32, times a negative 1/5, negative 32 fifths. Now, 8 is the same thing as 40 over 5. Take 40 over 5 minus 32 over 5, gives you 8 fifths. So now we have a nice constant that we'll integrate with respect to theta. And that'll give us 8 fifths times theta. And we take that from 0 to 2 pi. When you plug in the 2 pi for theta, 8 fifths times 2 pi gives you 16 pi over 5. And then you subtract what you get when you plug in 0 for theta. but that's just subtracting 0. So the final answer is 16 pi over 5. And with that, I have some recommended exercises I'd like to give you from 15.7. And those exercises are 1, 3, 9, 17, 21, and 29.